Joshua Angrist was born in 1960 in Columbus, Ohio, USA. He received his PhD in 1989 from Princeton University, USA. He is the full professor of economics at Massachusetts Institute of Technology, Cambridge, USA. So please welcome Joshua.
As I stilled my trembling iPhone early on October 11th, my thoughts went to the question of whether Nobel-level recognition might change life for the Angrist family. Ours is a close-knit family. We lack for nothing. So I worried that stressful Nobel celebrity might not be a plus. But with the first cup of coffee, I began to relax. It occurred to me that the matter of how public recognition affects a scholar's life is, after all, a simple causal question. The Nobel intervention is substantial, sudden, and well measured. Outcomes like health and wealth are easy to record. Having just been recognized with my co-laureates Guido Imbens and David Card for answering causal questions using observational data, my thoughts moved from personal upheaval to the more familiar domains of identification and estimation of causal effects. I was able to soothe my worried mind by imagining a study of the Nobel Prize treatment effect. How would such a study be organized? In a 1999 essay published in the Handbook of Labor Economics, Alan Kruger and I embraced the phrase empirical strategy. The handbook volume in question was edited by two of my Princeton PhD thesis advisors, Orly Ashenfelter and David Card, among the most successful and prolific graduate advisors economics has known. An empirical strategy is a research plan that encompasses data collection, identification, and econometric estimation. Identification is the applied econometrician's term for research design. A randomized clinical trial, an RCT, is the simplest and most powerful research design. In RCTs, causal effects are identified by the random assignment of treatment. Random assignment ensures that treatment and control groups are comparable in the absence of treatment, so differences between them afterwards reflect only the treatment effect. Nobel Prizes are probably not randomly assigned. This challenge notwithstanding, a compelling empirical strategy for the Nobel treatment effect comes to mind, at least as a flight of empirical fancy. Imagine a pool of prize-eligible Nobel applicants, the group under consideration for the prize. Applicants need not apply themselves. They are, I presume, nominated by their peer scholars. My fanciful Nobel impact study looks only at Nobel applicants, since these are all elite scholars. But that is only the first step. Credible applicants, I imagine, are evaluated by judges using criteria like publications, citations, nominating statements. I imagine this material is reviewed and assigned a numerical score using some kind of scoring rubric. Top scorers, up to 3 per field in any single year, win a prize. Having identified applicants and collected data on their scores, the next step in my Nobel impact study is to record the relevant cutoffs. The Nobel cutoff is the lowest score among those awarded a prize. Many Nobel hopefuls just miss the cutoff. Looking only at near misses, along with the winners, differences in scores between those above and below the cutoff begin to look serendipitous, almost randomly assigned. After all, near Nobels are among the most eminent of scholars, too. With one more high-impact publication, a little more support from nominators, they would have been awarded Nobel Gold. Some of them someday surely will be. The empirical strategy sketched here is called a regression discontinuity design, RD. RD exploits the jumps in human affairs induced by rules, regulations, and the need to classify people for various assignment purposes. When treatment or intervention is determined by whether a tie-breaking variable crosses a threshold, those just below the threshold become a natural control group for those who clear it. RD does not require the variable whose causes we seek switch fully on or off at the cutoff. We require only that the average value of this variable jump at the cutoff. RD can allow, for example, for the fact that this year's near Nobel might be next year's winner. Allowing for this leads to the use of jumps and the rate at which treatment is assigned to construct instrumental variables, IV, estimates of the effect of treatment received. This sort of RD is said to be fuzzy. But, as Steve Pischke and I wrote in our first book, Fuzzy RD is IV. The first RD study I contributed to was written with my frequent collaborator, Victor Levy. This study is motivated by the high costs and uncertain returns to smaller elementary school classes. We exploited a rule used by Israeli elementary schools to determine class size. This rule is used to estimate class size effects as if in a class size RCT. In the 1990s, Israeli classes were large. Students enrolled in a grade cohort of 40 were likely to be seated in a class of 40. That's the relevant cutoff. Add another child to the cohort, making 41, and the cohort was likely to be split into two much smaller classes. This leads to the Maimonides rule research design, so named because the 12th century Rambam proposed a maximum class size of 40. This figure plots Israeli fourth grade class sizes as a function of fourth grade enrollment, overlaid with the theoretical class size rule, Maimonides rule. The fit isn't perfect. That's a feature that makes this application of RD fuzzy. But the gist of the thing is a marked class size drop at each integer multiple of 40, the relevant cutoff, just as predicted by the rule. As it turns out, these drops in class size are reflected in jumps in 4th and 5th grade math scores. Would a comparison of Nobel laureates to near laureates really be a good natural experiment? The logic behind this sort of claim seems more compelling for comparisons of schools with 40 and 41 fourth graders than for comparisons of laureates and near laureates. Yet, both scenarios exploit a feature of the physical world. Provided the tie-breaking variable, known to RD mavens as the running variable, has a continuous distribution, the probability of crossing the cutoff approaches 1/2 when examined in a narrow window around the cutoff. In RD empirical work, the window around such cutoffs is known as a bandwidth. Importantly, this limiting probability is 0.5 for everybody, regardless of how qualified they look going into the Nobel competition. This remarkable fact can be seen in data on applicants to one of New York's highly coveted screen schools. By way of background, roughly 40% of New York City's middle and high schools select their applicants on the basis of test scores, grades, and other exacting criteria. In other words, the admissions regime for screen schools is a lot like the scheme I've imagined for the Nobel Prize. Screen schools are but one of a number of highly selective systems within a system in large U.S. school districts. Boston, Chicago, San Francisco, and Washington, D.C. all feature highly selective institutions, often known as exam schools. Exam schools operate as part of larger public school systems that enroll students without screening. Motivated by the enduring controversy over the equity of screened admissions, my Blueprint Labs collaborators and I have examined the causal effects of exam school attendance in Boston, Chicago, and New York. This figure shows the probability of being offered a seat at New York's storied Townsend Harris High School, ranked 12th nationwide. Bar height in the figure marks the qualification rate, that is, the likelihood of earning a Townsend Harris admission score above that of the lowest scoring applicant offered a seat. Importantly, the bars show qualification rates conditional on a measure of pre-application baseline achievement. In particular, the bars mark qualification rates conditional on whether an applicant has upper quartile or lower quartile 6th grade math scores. Townsend Harris applicants with high baseline scores are much more likely to qualify than applicants with low baseline scores. This isn't surprising. But in a shrinking symmetric bandwidth around the school's cutoff, qualification rates in the two groups converge. Qualification rates in the last and smallest groups are both remarkably close to 1/2. This is what we'd expect to see were Townsend Harris to admit students by tossing a coin, rather than by selecting only those who scored highly on the school's entrance exam. Even when admissions operates by screening, the data can be arranged so as to mimic an RCT. Few of the questions I've studied are more controversial than the question of access to public exam schools like the Boston Latin School, Chicago's Peyton and Northside Selective Enrollment High Schools, and New York's legendary Brooklyn Tech, Bronx Science, and Stuyvesant Specialized High Schools, which have graduated 14 Nobel laureates between them. Townsend Harris, the school we started with today, graduated 3 Nobels, including economist Ken Arrow. Exam school proponents see the opportunities these schools provide as democratizing public education. Wealthy families, they argue, can access exam school curricula in the private sector. Shouldn't ambitious low-income students be afforded the same chance at elite education? Critics of selective enrollment schools argue that, rather than expanding equity, exam schools are inherently biased against the Black and Hispanic students that make up the bulk of America's urban districts. New York's super-selective Stuyvesant, for example, enrolled only 7 Black students in 2019 out of an incoming class of 895. But are exam school seats really worth fighting for? My collaborators and I have repeatedly used our empirical strategies to study the causal effects of attendance at exam schools like Townsend Harris and Boston Latin. Our first exam school study, which looks at schools in Boston and New York, encapsulates these findings in its title, The Elite Illusion. The elite illusion refers to the fact that while exam school students undoubtedly have high test scores and other good outcomes, this is not a causal effect of exam school attendance. Our estimates consistently suggest that the causal effects of exam school attendance on their students' learning and college going are 0, maybe even negative. The good performance of exam school students reflects selection bias, that is, the process by which these students are chosen, rather than causal effects. Data from Chicago's large exam school sector illustrate the elite illusion. This figure plots peer mean achievement, that is, the 6th grade test scores of my 9th grade classmates, against the admissions tiebreaker for a subset of applicants to any one of Chicago's 9 exam schools. Applicants to these schools rank up to 6, while the exam schools prioritize their applicants using a common composite index formed from an admissions test, GPAs, and grade 7 standardized scores. This composite tiebreaker is the running variable for an RD design that reveals what happens when any applicant is offered an exam school seat. In Chicago's exam school match, which is actually an application of the celebrated Galen-Shapley matching algorithm, exam school applicants are sure to be offered a seat somewhere when they clear the lowest in their set of cutoffs among the schools they rank. We call this lowest cutoff the qualifying cutoff. The figure shows a sharp jump in peer mean achievement for Chicago exam school applicants who clear their qualifying cutoff. This jump reflects the fact that most applicants offered an exam school seat take it. And applicants who enroll at one of Chicago's selective enrollment high schools are sure to be seated in a 9th grade classroom filled with academically precocious peers, because only the relatively precocious make it in. The increase in peer achievement across the qualifying cutoff amounts to almost half a standard deviation, a very large effect. And yet, precocious peers notwithstanding, the offer of an exam school seat does not appear to increase learning. Let's plot applicants' ACT scores against their tiebreaker values. This plot shows that exam school applicants who clear their qualifying cutoff perform sharply worse on the ACT. What explains this? It takes a tale of IV and RD to untangle the forces behind this intriguing and unexpected negative effect. But first, some IV theory. Guido Imbens and I developed theoretical tools that enhance economists' understanding of empirical strategies involving IV and RD. The prize we share is in recognition of this work. Guido and I overlapped for only 1 year at Harvard, where we had both taken our first jobs post-PhD. I welcomed Guido to Cambridge, Massachusetts, with a pair of interesting instrumental variables. I had used the draft lottery instrument in my PhD thesis to estimate the long-run economic consequences of serving in the armed forces for soldiers who were drafted. The draft lottery instrument relies on the fact that lottery numbers randomly assigned to birthdays determined Vietnam-era conscription risk. Yet even then, most soldiers were volunteers, as they are today. The quarter of birth instrument is used in my 1991 paper with Alan Kruger to estimate the economic returns to schooling. This instrument uses the fact that men who are born earlier in the year are allowed to drop out of high school on their 16th birthday with less schooling completed than those born later. Guido and I soon began asking each other, What really do we learn from the draft eligibility and quarter-of-birth natural experiments? An early result in our quest for a new understanding of IV was a solution to the problem of selection bias in an RCT with partial compliance. Even in a randomized clinical trial, some of the people assigned to treatment may opt out. This fact has long vexed trialists because decisions to opt out are not made by random assignment. Our first manuscript together shows that in a randomized trial with partial compliance, you can use IV to estimate the effect of treatment on the treated, even when some offered treatment decline it. This works in spite of the fact that those who comply with treatment may be a very select group. Unfortunately for us, we were late to the party. Not long after releasing our first working paper, we learned of a concise contribution from Howard Bloom that includes this theoretical result. Remarkably, Bloom had derived this from first principles without making a connection to IV. So Guido and I went back to the drawing board, and a few months later we had LATE, a theorem showing how to estimate the local average treatment effect. The LATE theorem generalizes the Bloom theorem and establishes the connection between compliance and IV. Maintaining the clinical trials analogy, let ZI indicate whether subject I is offered treatment. This is randomly assigned. Also, let D1I indicate subject I's treatment status when assigned to treatment, and let D0I indicate subject I's treatment status when assigned to control. I'll use this formal notation to give a clear statement of the LATE result, and then follow up with examples. A key piece of the LATE framework, pioneered by statistician Don Rubin, is the pair of potential outcomes. As is customary, I denote potential outcomes for subject I in the treated and untreated states by Y1I and Y0I, respectively. The observed outcome is Y1I for the treated and Y0I for those not treated. Y1I minus Y0I is the causal effect of treatment on individual I, but this we can never see. We try, therefore, to estimate some kind of average causal effect. The LATE framework allows us to do that in an RCT where some controls are treated. The theorem says that the average causal effect on people whose treatment status can be changed by the offer of treatment is the ratio of ITT to the treatment control difference in compliance rates. A mathematical statement of this result appears here, where Greek letter delta symbolizes the ITT effect, and Greek symbols pi1 and pi0 are compliance rates in the group assigned to treatment and the group assigned to control, respectively. The print version of this lecture delves deeper into LATE intellectual history, highlighting key contributions made with Rubin. For now, though, I'd like to make the LATE theorem concrete for you by sharing one of my favorite applications of it. I'll explain the LATE framework through a research question that has fascinated me for almost 2 decades. What is the causal effect of charter school attendance on learning? Charter schools are public schools that operate independently of traditional American public school districts. A charter, the right to operate a public school, is typically awarded for a limited period, subject to renewal, conditional on good school performance. Charter schools are free to structure their curriculum and school environment. The most controversial difference between charters and traditional public schools is the fact that the teachers and staff who work at charter schools rarely belong to labor unions. By contrast, most big city public school teachers work under union contracts. The 2010 documentary film Waiting for Superman features schools belonging to the Knowledge is Power program, KIPP. KIPP schools are emblematic of the high expectations, sometimes also called no excuses, approach to public education. The no excuses model features a long school day, an extended school year, selective teacher hiring, and focuses on traditional reading and math skills. The American debate over education reform often focuses on the achievement gap. That's shorthand for large test score differences by race and ethnicity. Because of its focus on minority students, KIPP is often central in this debate, with supporters pointing to the fact that non-white KIPP students have markedly higher test scores than non-white students from nearby schools. KIPP skeptics, on the other hand, argue that KIPP's apparent success reflects the fact that KIPP attracts families whose children would be more likely to succeed anyway. Who's right? As you've probably guessed by now, a randomized trial might prove decisive in the debate over schools like KIPP. Like Nobel Prizes, though, seats at KIPP are not randomly assigned. Well, at least, not entirely. In fact, Massachusetts charter schools with more applicants than seats must offer their seats by lottery. Sounds like a good natural experiment. A little over a decade ago, my collaborators and I collected data on KIPP admissions lotteries, laying the foundation for two pioneering charter studies, the first to use lotteries to study KIPP. Our KIPP analysis is a classic IV story because many students offered a seat in the KIPP lottery failed to show up in the fall, while a few not offered a seat nevertheless find their way in. This graphic shows KIPP middle school applicants' math scores 1 year after applying to KIPP. The entries above the line show that KIPP applicants who were offered a seat have standardized math scores close to 0, that is, near the state average. As before, we're working with standardized score data that has a mean of 0 and a standard deviation of 1. Because KIPP applicants start with 4th grade scores that are roughly 0.3 standard deviations below the state mean, achievement at the level of the state average is impressive. By contrast, the average math score among those not offered a seat is about minus 0.36 sigma, that is 0.36 standard deviations below the state mean, a result typical for urban students in Massachusetts. Since lottery offers are randomly assigned, we could say with confidence that the offer of a seat at KIPP boosts math scores by an average of 0.36 sigma, a large effect that's also statistically precise. We can be confident this isn't a chance finding. What does an offer effect of 0.36 sigma tell us about the effects of actually going to KIPP? IV methods convert KIPP offer effects into KIPP attendance effects. I'll use this brief clip from my Marginal Revolution University short course to quickly review the key assumptions behind this conversion.
IV describes a chain reaction. Why do offers affect achievement? Probably because they affect charter attendance, and charter attendance improves math scores. The first link in the chain, called the first stage, is the effect of the lottery on charter attendance. The second stage is the link between attending a charter and an outcome variable, in this case, math scores. The instrumental variable, or instrument for short, is the variable that initiates the chain reaction. The effect of the instrument on the outcome is called the reduced form.
IV eliminates selection bias, but like all of our tools, the solution builds on a set of assumptions not to be taken for granted. First, there must be a substantial first stage. That is, the instrumental variable, winning or losing the lottery, must really change the variable whose effect we're interested in, here, KIPP attendance. In this case, the first stage is not really in doubt. Winning the lottery makes KIPP attendance much more likely. Not all IV stories are like that. Second, the instrument must be as good as randomly assigned, meaning lottery winners and losers have similar characteristics. This is the independence assumption. Of course, KIPP lottery wins really are randomly assigned. Still, we should check for balance and confirm that winners and losers have similar family backgrounds, similar aptitudes, and so on. In essence, we're checking to ensure KIPP lotteries are fair, with no group of applicants suspiciously likely to win. Finally, we require the instrument change outcomes solely through the variable of interest, in this case attending KIPP. This assumption is called the exclusion restriction. The causal effect of KIPP attendance can therefore be written as the ratio of the effect of offers on scores in the numerator over the effect of offers on KIPP enrollment in the denominator. The numerator in this IV formula, that is the direct effect of the instrument on outcomes, has a special name. This is called the reduced form. The denominator is the first stage. The exclusion restriction is often the trickiest or most controversial part of an IV story. Here, the exclusion restriction amounts to the claim that the 0.36 score differential between lottery winners and losers is entirely attributable to the 0.74 win-loss difference in attendance rates. Plugging in the numbers, the effect of KIPP attendance works out to be 0.48 sigma, almost half a standard deviation gain in math scores. That's a remarkably large effect. Who exactly benefits so spectacularly from KIPP? Does everyone who applies to KIPP see such large gains? Late answers this question. The late interpretation of the KIPP-IV empirical strategy is illuminated by the biblical story of Passover, which explains that there are 4 types of children, each with characteristic behaviors. To keep track of these children and their behavior, I'll give them alliterative names. Applicants like Alvaro are dying to go to KIPP. If Alvaro loses the KIPP lottery, his mother finds a way to enroll him in KIPP anyway, perhaps by reapplying. Applicants like Camilla are happy to go to KIPP if they win a seat in the lottery, but stoically accept the verdict if they lose. Finally, applicants like Normando worry about long days and lots of homework at KIPP. Normando doesn't really want to go and refuses to go to KIPP when told that he won the lottery. Normando is called a never-taker because win or lose he doesn't go to KIPP. At the other end of KIPP commitment, Alvaro is called an always-taker. He'll happily take a seat when offered, while his mother simply finds a way to make it happen for him, even when he loses. For Alvaro and Normando both, choice of school, KIPP, traditional, is unaffected by the lottery. Camilla is the type of applicant who gives IV its power. The instrument determines her treatment status. IV strategies depend on applicants like Camilla, who are called compliers. This term comes from the world of randomized trials introduced earlier. As we've already discussed, many randomized trials randomize only the opportunity to be treated, while the decision to comply with the treatment remains voluntary and non-random. RCT compliers are those who take treatment when the offer of treatment is made, but not otherwise. With lottery instruments, late is the effect of KIPP attendance on Camilla and other compliers like her who enroll at KIPP, take treatment, when offered treatment through the lottery, but not otherwise. IV methods are uninformative for always-takers like Alvaro and never-takers like Normando because the instrument is unrelated to their treatment status. Hey, didn't I say there are 4 types of children? A 4th type of child in IV theory behaves perversely. Every family has one. These defiant children enroll in KIPP only when they lose the lottery. Actually, the late theorem requires us to assume there are few defiers. That seems like a reasonable assumption for charter lottery instruments, if not in life. The late theorem is sometimes seen as limiting the relevance of econometric estimates because it focuses attention on groups of compliers. Yet the population of compliers is a group we'd very much like to learn about. In the KIPP example, compliers are children likely to be drawn into KIPP were the school to expand and offer additional seats in a lottery. How relevant is this? A few years ago, Massachusetts indeed allowed thriving charter schools to expand. A recent study by some of my lab mates shows that late estimates like the one we just computed for KIPP predict learning gains at the schools created by charter expansion. Late isn't just a theorem, it's a framework. The late framework can be used to estimate the entire distribution of potential outcomes for compliers, as if we really did have a randomized trial for this group. Although the theory behind this fact is necessarily technical, the value of the framework is easily appreciated in practice. By way of illustration, recall that the KIPP study is motivated in part by differences in test scores by race. Let's look at the distribution of 4th grade scores, separately by race, for applicants to Boston charter middle schools. The 2 sides of this figure show distributions for treated and untreated compliers. Treated compliers are compliers offered a charter seat in a lottery, while untreated compliers are not offered a seat. Because these are 4th grade scores, while middle school begins in 5th or 6th grade, the 2 sides of the figure are similar. Both sides show score distributions for black applicants shifted to the left of the corresponding score distributions for whites. By 8th grade, treated compliers have completed middle school at a Boston charter, while untreated compliers have remained in traditional public school. Remarkably, this next graphic shows that the 8th grade score distributions of black and white treated compliers are indistinguishable. Boston charter middle schools close the achievement gap. But for the untreated, black and white score distributions remain distinct, with black students behind white students, as they were in 4th grade. Boston charters close the achievement gap because those who enter charter schools the farthest behind tend to gain the most from charter enrollment. I elaborate on this point in the print version of this talk. Remember the puzzle of negative Chicago exam school effects? I'll finish the scientific part of my talk by using IV and RD to explain this surprising finding. The resolution of this puzzle starts with the fact that economic reasoning is about alternatives. So what's the alternative to an exam school education? For most applicants to Chicago exam schools, the leading non-exam alternative is a traditional public school. But many of Chicago's rejected exam school applicants enroll in a charter school. Exam school offers therefore reduce the likelihood of charter school attendance. Specifically, exam schools divert applicants away from high schools in the Nobel network of charter schools. Nobel, with pedagogy much like KIPP, is one of Chicago's most visible charter providers. Also like KIPP, convincing evidence on Nobel effectiveness comes from admissions lotteries. The x-axis in this graphic shows lottery offer effects on years enrolled at Nobel. This is the Nobel first stage, for an IV setup that uses a dummy indicating Nobel lottery offers as an instrument for Nobel enrollment. Now this graphic has a feature that distinguishes it from the simpler KIPP analysis. The plot shows first stage effects for two groups, one for Nobel applicants who live in Chicago's lowest income neighborhoods, Tier 1, and one for Nobel applicants who live in higher income areas, Tier 3. Remember the IV chain reaction? Each point in this graphic has coordinates given by first stage reduced form, and therefore implies an IV estimate. The effect of Nobel enrollment on ACT scores is the ratio of reduced form coordinate to first stage coordinate. The graphic shows two such ratios. The relevant results for Tier 1 are 0.35, while for Tier 3 we have 0.33. Not bad. For Nobel applicants from both tiers, these first stage and reduced form estimates imply a yearly Nobel enrollment effect of about 1/3 of a standard deviation gain in ACT math scores. Notice there's also a line connecting the two IV estimates in the figure. Because this line passes through the origin, its slope, rise over run, is about equal to the two IV estimates. In this case, the slope is about 0.34. The fact that the line passes through 0, 0 is significant for another reason. By this fact, we've substantiated the exclusion restriction. Specifically, the exclusion restriction says that, given a group for which Nobel offers are unrelated to Nobel enrollment, we should expect to see zero reduced form effect of these offers made to applicants in that group. How consistent is the evidence for a Nobel-caused learning gain on the order of 0.34 sigma per year? In this next graphic, we've added 12 more points to the original 2. The red points here show first stage and reduced form Nobel offer effects for 12 additional groups, 2 more tiers, and 12 groups defined by demographic characteristics related to race, sex, family income, and baseline scores. Although not a perfect fit, these points cluster around a line with slope 0.36 sigma, much like the line we saw earlier for applicants from tiers 1 and 3. You're likely now wondering what the Nobel IV estimates in this figure have to do with exam school enrollment. Here's the answer. The blue line in this new graphic shows, as we should expect, that exam school exposure jumps up for applicants who clear their qualifying cutoff. At the same time, the red line shows that Nobel school enrollment clearly falls at the same point. This is the diversion effect of exam school offers on Nobel enrollment. Many kids offered an exam school seat prefer that exam school seat to enrollment at Nobel. IV affords us the opportunity to go out on a limb with strong claims about the mechanism behind the causal effect. Here's a strong causal claim regarding why Chicago exam schools reduce achievement. The primary force driving reduced form exam school qualification effects on ACT scores, I claim, is the effect of exam school offers on Nobel enrollment. In support of this claim, Consider the points plotted here in blue, all well to the left of 0 on the x-axis. These points are negative because they mark the effect of exam school qualification on Nobel school enrollment for particular groups of applicants. Now, we've already seen that Nobel applicants offered a Nobel seat realized large ACT math gains as a result. Now consider exam school offers as an instrument for Nobel enrollment. As always, IV is a chain reaction. If exam school qualification reduces time at Nobel by 0.37 years, and each year of Nobel enrollment boosts ACT math scores by about 0.36 sigma, we should expect reduced form effects of exam school qualification to reduce ACT scores by the product of these two numbers, that is, by about 0.13 sigma. The reduced form qualification effects at the left of the figure are broadly consistent with this. They cluster closer to minus 0.16 than to minus 0.13, but that difference is well within the sampling variance of the underlying estimates. The causal story told here postulates diversion away from charter schools as the mechanism by which exam school offers affect achievement. In other words, it's Nobel enrollment that's presumed to satisfy an exclusion restriction when we use exam school offers as an instrumental variable. Importantly, as we saw before, the line in this final graphic with two sets of 14 points runs through the origin. This fact supports our new exclusion restriction. For any applicant group for which exam school offers have little or no effect on Nobel school enrollment, we should also see ACT scores unchanged. At the same time, because the blue and red dots cluster around the same line, the IV estimates of Nobel school enrollment effects generated by both Nobel and exam school offers are about the same. I hope this empirical story convinces you of the power of IV and RD to generate new causal knowledge. For decades, I've been lucky to work on many equally engaging empirical problems. I computed the draft lottery IV estimates in my Princeton PhD thesis on a big, hairy mainframe monster using 9-track tapes and leased space on a communal hard drive. Princeton graduate students learned to mount and manipulate tape reels the size of a cheesecake. Thankfully, empirical work today is a little less labor-intensive. What else has improved in the modern empirical era? In a 2010 article, Steve Pischke and I coined the phrase credibility revolution. By this we mean economics shift towards transparent empirical strategies applied to concrete causal questions, like the questions David Card has studied so convincingly. The econometrics of my school days focused more on models than on questions. The modeling concerns of that era have mostly faded, but econometricians have since found much to contribute. I'll save my personal lists of greatest hits and exciting new artists for the print version of this lecture. I'll wrap up here by saying that I'm proud to be part of the contemporary empirical economics enterprise, and I'm gratified beyond words to have been recognized for contributing to it. Back at Princeton in the late 80s, my graduate school classmates and I chuckled reading Ed Lemer's lament that no economist takes another economist's empirical work seriously. This is no longer true. Empirical work today aspires to tell convincing causal stories. Not that every effort succeeds, far from it. But, as any economics job market candidate will tell you, empirical work carefully executed and clearly explained is taken seriously indeed. That is a measure of our enterprise's success.